Hi everyone, and welcome to the second of two videos going through some past exam questions on the topic of entropy and free energy. The questions we're going to go through in this video are actually very similar to the first video, which is good news because it shows that there's really only 3 or 4 different types of questions they can ask you on this topic, and they just repeat the same questions over and over again. So if you can practice these questions, you can hopefully get to the point where you're confident and you know what you're doing. Again, it's starting off with a wordy question where we've got to predict the entropy changes. So again, it's saying we're looking at entropy. 3 processes are given below. State and explain whether the change would be accompanied by an increase or decrease in entropy. So this is very similar to the first question in the previous video. So if we freeze water, what's going to happen here? So we're going to be doing a change of state. Let's do the explanation first. That will lead to the answer. So if we freeze water, there's a change of state from liquid to solid. So if we're going from liquid to solid, it's going to become less disordered. A solid is more organized, isn't it? Change of state from liquid to solid. So disorder decreases. And therefore, if it's becoming less disordered, then there should be a decrease in entropy. We could say delta S will be less than 0. Delta S will be negative. In the reaction of calcium carbonate with hydrochloric acid. Okay, so what's going on here? If we react, we need to work out what the products are going to be. So this is going to make, it's an acid and a carbonate, so it's going to make a salt and water and carbon dioxide. So it's going to make calcium chloride and water and carbon dioxide. So what's the relevance here? The relevance is it's making carbon dioxide gas, and we didn't have any gas to start with. Okay, so we could say this reaction produces a gas, and we can say it's CO2 just to show we know that. So disorder increases. The gas is the most disordered state, isn't it? So therefore there should be an increase in entropy. It's becoming more disordered. So delta S would be greater than 0. Right, and then finally this one, the formation of O3 from O2. This is a bit awkward then, because we've got gases on both sides. For this, you want to actually write the equation, really. We could have written the equation for this one. That would have been a reasonable idea, but we didn't really need to. I think we could do that in our head. This one, it's worth writing this out. So if I'm making O3 from O2, so I'm going from O2 to O3, then I'm going to balance that by doing 3 O2. It makes 2 O3, right? So now we can see what's going on. That we're going from 3 moles of gas to 2 moles of gas. Okay. So we can say 2 moles of gas are formed from 3 moles of gas. So the disorder is decreasing. Okay, we're going from 3 moles to 2 moles, so this is now less disordered than it was before. So we'd get a decrease in entropy. And we'd expect delta S to be less than 0. Okay. As we said before, it's usually good if you can do an explanation involving disorder, so you're showing that you know what entropy is, and put the numbers of moles in if you can. I think that's a good practice to get into. Okay, then we've got a slightly different, this is a question that we didn't see in the previous video, so it's worth just spend a little bit of time talking about this one. So it says the enthalpy and the entropy changes of a reaction both have a negative sign. Discuss how the feasibility of this reaction will change as the temperature increases. Okay, so if we're saying they both have a negative sign, so we're saying that delta H is negative, and we're saying delta S is negative. And when it says discuss how the feasibility of the reaction will change, then feasibility is to do with Gibbs energy, isn't it? Free energy. So we're using our equation here. So if they're both negative, what's going to happen with delta G? We're going to be doing a negative number, take away another negative number. So delta G might be positive or it might be negative. It's going to depend on the size of these two. If this is bigger, we're going to be taking away a bigger number. So like if I might be doing, let's just put some numbers in. Let's just scribble something down here for you. I'll answer the question. So we're going to be doing something like -2 take away -1, let's say. So if we do something like that, then we're doing -2 plus 1. So it's going to be -1. So that would be feasible because delta G would be less than 0. But what's going to happen as the temperature increases? So as the temperature gets bigger, it's going to make this part bigger, isn't it? And this is going to become like -2 take away -3. And then we're going to do -2 plus 3, so that would be +1. So therefore it would be not feasible. Okay, so as the temperature is going to get bigger, it's going to multiply the value of delta S, make this number into a bigger negative number, and therefore that's going to end up making delta G less feasible by the time you calculate it. Okay, so how are we going to word that? We need to be a little bit careful because we've got negative numbers with how we word this. So we want to say as the temperature increases, the best way to word this is to say that the value of T delta S becomes more negative. Yeah, and that's what we showed here, isn't it? If this gets bigger, it's going to get more negative. This results in the value of delta G becoming less negative. Which might actually end up becoming positive. So what does that mean for the feasibility? If delta G is becoming less negative, it means the reaction is going to become less feasible. So this results in the value of delta G becoming less negative, so the reaction is less feasible as temperature increases. Okay. So that's the pattern if you've got a negative delta H and a negative delta S. Okay. Interestingly, if these are both positive, it's the opposite way around. Okay. If these are both positive values, then the reaction becomes more feasible as the temperature increases. Okay. If delta H is negative and delta S is positive, then the reaction is always feasible. And if delta H is positive and delta S is negative, then the reaction is never feasible. Okay, and you can see that just by putting positive and negative values into this and seeing will delta G come out as greater or less than 0. Okay, so again, we've got a mixture of some wordy questions there and then some calculations. And again, these are very similar calculations to the previous video on this topic. So here we've been given some sort of reaction with tungsten, okay, whatever. Standard entropies are in this table. Calculate the free energy change. Okay, so if we want to calculate delta G, we need to do delta G is delta H minus T delta S. We're doing this equation again. So we know what delta H is. We're going to have to calculate delta S first, right? Because they've given us the entropy values. So we're going to have to do that first. So delta S, remember we're doing the products minus the reactants. So we're going to do tungsten, which is 33, plus 3 H2O, so it's 3 lots of that, minus the WO3, which is 76, and then also take away 3 lots of 131. Yeah, let's just check. So those are the products times that by 3 minus all of that lot. So minus that, yeah. Okay. So let's just work this out. Minus 76 minus 3 times 131. So we get a value of 131. Okay, and we always want to put the units on, so that would be in joules per Kelvin per mole. Right, then we want to come and do this calculation. Okay, but this is why the units matter. We don't want this in joules and this in kilojoules, so we're going to need to sort this out first. So 131 divided by 1,000. So it's going to be 0.131 kilojoules per Kelvin per mole. Now we can use this. So delta G is delta H, which is plus 115, minus the temperature. So it's 25 degrees. So we're going to add 273. So it's going to be 298 Kelvin. You'll get used to this, hopefully, because it's 25 degrees most of the time, because it's standard temperature. So it's going to be 298 times 0.131. So we'll do that first. Right, and we get an answer of 75.962. That is in kilojoules per mole, and that's a positive answer. I'm going to put a sign on it, so I think it's always a good idea. It doesn't say anywhere in the question about significant figures or anything, so we could just use that value. That would be fine. Right, and then the last bit here says calculate the minimum temperature at which the reaction becomes feasible. Okay, and we saw how to do this in the previous video, that we're looking for the cutoff point at which it does become feasible. Okay, because this is showing that at 25 degrees, the reaction's not feasible because delta G is coming out as positive. So to work out where's the cutoff point, it's when delta G is equal to 0. That's when it starts to become feasible. So therefore delta H minus T delta S is equal to 0. So therefore delta H is equal to T delta S. So therefore the temperature is delta H divided by delta S. And you'll get familiar with that rearrangement, hopefully, because it's the same every time. Whenever you see minimum temperature, you go, right, set it to 0, rearrange it like this. I always just write it out. I mean, it takes like 1 minute, I think, not even that. So it's worth writing, because sometimes you get marks for actually showing this. So I think it's worth doing this rather than just jumping straight to this point. And certainly if you get the wrong answer, you'll certainly pick up marks if you've done this. And now we can just substitute the values in. So delta H was our 115. And delta S was 0.131. Okay. And remember, when we calculate this, it's going to come out in Kelvin, which is what we want. They don't want us to convert it, so we need to be careful there. We just need to use this number. So it comes out as 877.9, so we'll call that 878 Kelvin. Okay, and that's going to be our answer. Yeah, we don't need to convert into degrees C.